This is 8.9 L. Oops, started looking at the wrong one there. Okay, so again, I want to start the same way by counting what I have. So I have copper, hydrogen, nitrogen, and oxygen. On the left, I've got 1 copper, 1 hydrogen, 1 nitrogen, and 3 oxygen. How do I know that this 3 here on the HNO3 means I only have 3 oxygen and not 3 hydrogen or 3 nitrogen? What? Right. It's a subscript, and it's a subscript for the oxygen. If I had 3 nitrogen and 3 hydrogen in that compound as well, it would have to be shown like this. H3N3O3. That would be 3 of each. Or, if I had HNO and I had a 3 here, that would be 3 of each. Or it could be HNO with a 3 here. That would be 3 of each. Right, so you want to make sure you're familiar with all the different ways that numbers can be used to increase how many of each element are present. So if I don't have any of those situations, I just have the subscript 3 next to the oxygen. It means it's only the oxygen that I have 3 of. So I want to count on the other side. On the other side, I have 1 copper. How many total nitrogen? 3. Well, I should have went to hydrogen first. 3 nitrogen. I've got 2, because of this 2 is giving me 2 NO3 groups, plus 1 more from the NO next to it. Hydrogen, I have 2 from the water, and oxygen I have 8. Right, 2 times 3 here, so that's 6, plus 1 more here, plus 1 more here is 8. So copper is the only one balanced here, so I obviously would not start by changing that. I might have to change it later if it becomes imbalanced in the process of balancing other elements, but I want to start with something else. So if I can tell that I only have an element appearing in 2 locations and it's not already balanced, that's probably the easiest one to balance. So since I've got oxygen appearing in multiple areas, I probably don't want to start by balancing that. And since I've got nitrogen in a couple different compounds on the right-hand side, I might not want to start by balancing that either. Maybe I want to start by balancing the hydrogen. There's only hydrogen appearing in 2 locations. So maybe I'd start with that. So maybe I'd recognize I've got 2 hydrogen on the right, so I want 2 on the left. So if I change that coefficient, again, when we're balancing, we only change the coefficients. We're never changing any of the subscripts, because that would mean we have a completely different reaction with different substances. But this reaction is defined by the substances involved, so we can't change the identities of the substances. That would give me 2 hydrogen now, 2 nitrogen, and 6 oxygen. So now I've got the hydrogen balanced, but the nitrogen is not balanced. So what I'm finding here is even when I increase that number, I still don't have enough nitrogen on the left to balance out what I have on the right. And there's only one compound the nitrogen appears in on the left-hand side. So the only way to get the nitrogen balanced is to increase the amount I have on the left and increase the amount I have on the right. But if I increase this number here to get more nitrogen, then the hydrogen won't be balanced anymore. So is there anything I can do that will increase the amount of nitrogen here to get it balanced on both sides but we'll also keep the hydrogen balanced at the same time. So if I could find a coefficient that would increase the amount of nitrogen there, and then also a coefficient, well, so basically what I'm talking about here is if I increase this number now to a 3, now I've got 3 nitrogen on both sides, but the hydrogen aren't balanced anymore. And there's no way I can get this hydrogen to be exactly equal to 3. So I can kind of work through this continuing in a kind of trial and error methodology. And if I do that, then I'll just have to kind of keep increasing the numbers until they start to become more balanced. So if I did increase that to a 3, and now I have 3 hydrogen on the left, I can't get 3 hydrogen on the right because of the H2O. No matter how I increase this number in front of the water, I'm always going to increase the number of hydrogens by 2 on that side. So I've got to get this number back over here into an even number so that now when I increase the hydrogen on the other side, they could potentially be equal. So I did a couple things. So I want to go through and double check all my numbers here. I changed all this stuff. So now on the left, I've got 4 hydrogens, 4 nitrogens, and 12 oxygens. On the right, I've got 4 hydrogens, 3 nitrogens, and 6, 7, 8, 9 oxygens. So maybe it feels like I'm getting closer, maybe it doesn't. I'm definitely not there yet. So at this point, I've got too much nitrogen and oxygen on the left. I need more on the right. Yes? Yeah, so what he's saying is he's focusing on the oxygen. If I've got 12 on the left and I've only got 9 on the right, I need more. Plus, if I need more of both the nitrogen and the oxygen, there's a compound, the NO, that contains both of those. So if I could maybe increase just the amount of that compound, I could get it balanced. So if I do put a 3 here, that might be helpful. Yeah. Change the subscript? No, I can't change the subscript. No, because then it's not the same compound. So the reason there's a 2 there as a subscript is because the copper has a +2 charge, and the NO3 has a -1 charge. And so I need 2 of the -1s to keep the +1 balanced if I'm going to make that compound. So the subscripts are there for a chemical reason based on the stability of the substance. If you change the subscripts, you're not going to be likely to have a stable substance anymore. And so, if these things react, they'll react in a way where the electrons can arrange in some stable way to complete octets and make the substances as stable as possible. So we can't change that, or it's not going to be a stable reaction. So let's go back to before we change this number. So what should I do at this point? Ideally, a change in the coefficient for the NO would be nice, because if I could change the coefficient for the NO and increase the nitrogen and the oxygen until everything's balanced, that would be wonderful, but I can't actually do that because the NO is in a 1-to-1 ratio in that compound. But I only need 1 more nitrogen on the right and 3 more oxygens. So there's no way to get just 1 more nitrogen and 3 more oxygens. If I put a 2 in front of this, then I increase the number of nitrogens by 1 from what I had, and the oxygens by 1, but I need more oxygens. So if I increase this number even more, then I've got too many nitrogens. So one other kind of hint that you can look for is when you see a group of elements that are bonded together and they're staying together as a group, a lot of times you can look at that as a group, and that can, if you keep that group together in your mind, you can try to balance the number of NO3s on both sides. So what I did here was I increased on the left. Well, actually, that is a good hint that usually works. It's not going to work here, though, because the nitrogen, some of the nitrogen of the NO3 is not staying together, obviously, if it's producing NO on the right-hand side. So that idea is, it will often work, but it's not going to work here. So what do I need to do? You added a 6 in front of the HNO3?
Yes.
Okay.
Because then you can manipulate how much oxygen you have, because you have two that are long sections, you know what I mean? So you can manipulate from there.
Yeah. Okay, that's a reasonable idea. I don't know if that would be instinctual for most people, since at this point we already have more nitrogen and oxygen on the left than we do on the right. And so if you increase that number, you're going to make it even more. But if what we have isn't working, because we can't get the same number on the right that we currently have on the left just by adding a number, you know, if we then change what we have on the left, it might make it easier to figure out how to change what we have on the right to match it. Do you have an idea?
You add a coefficient to the CU3
Right. So that's another idea. So what we're seeing here is we don't have enough nitrogen and oxygen to match what we have on the left. So my instinct was to increase the amount of nitrogen and oxygen here in the NO, but we just saw that we can't do that in a way that will fix both of those elements and keep both of them balanced. So what Miles is saying is if I change the coefficient here, that will also change the amount of nitrogen and oxygen. It might help fix it. But then if I change the amount of copper, I can easily fix that, since copper appears by itself on the left-hand side. So maybe we'll try that. So if I change this to a 2, that will change everything here except the hydrogen, which is good because I've already got the hydrogen balance. So now I've got 2 copper. How many nitrogen now do I have on the right-hand side of the arrow? I've got 5. I've got 2 times 2 for the nitrogen there, plus 1 more in the NO. That's 5. And how many total oxygen? So this is 2 times 3, 6. But I've got 2 of those. So I've got to multiply that by 2 again. So that's 12 plus 1. That's 13 plus 2 more, 15. So now I've got too many nitrogen and oxygen on the right. If I want to get more nitrogen and oxygen on the right, or if I want to get more on the left to balance that, maybe I want to change this to a 5. What? Right. Right, so if I do that, it might help me get closer with the nitrogen and oxygen. But what I'll realize is, as we said earlier, I can't have an odd number here in front of the HNO3 because I won't ever be able to keep the hydrogen balanced. So then maybe we need to go all the way to a 6 like Zach had anticipated. So if I do that, Then I already know I'm going to have to change this to a 3 to get the hydrogens balanced. So let's take a look at where we are then. Also, I might as well throw a 2 in here since I've got 2 copper on both sides and see where that gets me. So now on the left I've got 2 copper, 6 hydrogen, 6 nitrogen, and 6 times 3, 18 oxygen. On the right I have 2 copper, I've got 4 nitrogen from the first compound, 1 from the second, so that's, I want to go to hydrogen next. I've got 6 hydrogen from the 3 waters. I've got, so then for nitrogen, I've got 1 from the NO. I've got 4 from the other compound, so that's 5. And for oxygen, I've got 12, 13, 14, 15, 16. Is that right? 6, 12. Yeah, that's right. That seems right. So, getting a little closer maybe. What else can I do here? If I make the NO a 2, I will be getting a little bit closer, but if I put a 2 here, that's going to give me 1 more nitrogen, so that'll help. But that gives me 17 oxygen instead of 18. So that may not be what I want to do there. Any other ideas? Did I write the question down wrong? Double check that. Seems right. Yeah, I might have to do that. So maybe let's take a look at that. You know, there's a lot of trial and error involved. If I do that, I'm going to need 3 here, obviously, to keep the copper balanced. So let's look at where that puts us. On this side, I would have 7 nitrogen, so that's not going to work with the 6 I have. So that would give me 3 times 2, 6, 18, 22 oxygen. So if I change that to a 7, I'll change it to an 8. So that puts me at 8 hydrogen and 23 oxygen. Yes. No, it's just NO, I think. Yeah, so after all that trouble, now I'm finally there because I need one more NO and one more O on the right hand side, and I can get that by increasing the number of NO by one more than it was. So now if I count everything up, I'll have 8 here and 24 here. So that one was a pretty complicated one. So most of the ones that you'll balance will not be nearly that difficult. But the point is illustrated that there's no mathematical formula where you can just plug in an equation and know how to balance it. I mean, there may actually be an app for that. I don't know. But on the exam, you won't have that. So it's a trial and error process. You've got to start by balancing some things and seeing how it unbalances other things, and try different numbers. And when you have too much of something on one side, increase it on the other side by increasing one of the coefficients. And just try to keep getting closer and closer. And what you'll find, what we did here, is what happens a lot. If I increase it on one side, then I have too much. So then I increase the other side, but then it becomes too much, and I have to increase the other side again. And sometimes you have to go back and forth until you can find just the right number to put in for one of the compounds that will increase the number just enough to then finish the balancing. If you end up with a situation like this where you have a lot of numbers, though, go back through and look at them all to make sure you can't reduce them down. Because that happens a lot of times. Students get a little carried away and the numbers get really large all of a sudden. Is there any number that we can divide all of those coefficients by and without creating any fractions? No. So a lot of times you find, oh, I can divide all the numbers by 2 and reduce them down and not create any fractions. That's not the case in this case. So this is the smallest whole numbers we can actually put in there to balance it. Question?
Yeah, I was going to ask, how does this apply? Like, what are we actually doing?
Yeah, good question. So the point of balancing it, there's a couple important points about balancing. One is the reason we're doing this is because if you go into the lab and you take copper and HNO3 and you put them together, you want to know what you're going to get. So without all these coefficients, if you just had the compounds given, you could predict the substances that you would create. Right? It doesn't have to be balanced for you to predict the substances that you would create. The point of balancing is to be able to quantify that. So I know if I do this reaction in the lab, for every 3 atoms of copper I have, I need 8 molecules of HNO3 to react at all. If I don't put at least 8 molecules of HNO3 in for every 3 atoms of copper, I won't be able to react all the copper that I have. Maybe I don't want to. Maybe I only want to react half the copper. Well, how much ever I want to react, I can calculate exactly how much HNO3 I need to put in with it. And since we know also we use the term mole to describe the quantity of things as well, I also can say if I have 3 moles of copper, I need 3 moles of HNO3. And since the periodic table, the masses on the periodic table give us a relationship between moles and grams, that also allows us then, when we have the balanced reaction, to calculate how many grams of something I might need to weigh out in order to have a reaction to take place. If I've got 20 grams of copper and I want to get that all to react, how much HNO3 do I need? Well, I'd need to convert the 20 grams of copper into moles, and then recognize for every mole of copper I need 8 moles of HNO3, and then convert that back to grams so I know how many grams of HNO3 I need to add. So the balanced reaction is extremely useful in terms of recognizing the molar relationship between different substances in the reaction. If I had 4 moles of HNO3 reacting, I can also know that I would be able to produce 2 moles of water from that because of the ratio that I get from the balanced reaction.